right, this video will cover the concepts in section 10.2. Section 10.2, how to find the area of a regular n-gon. And it also has the area and circumference of circles in there as well. All right, we're going to consider some specific cases in terms of a side length S. And then eventually we'll generalize the idea and do 3 or 4 good examples. So let's start with a regular three-gon, a regular triangle whose sides are S. All right, how to find its area? Well, we know that the area of the triangle is 1/2 times the base times the height. And we can treat S as the base, which means we need to find the height. How high is this triangle's altitude? All right, well, an equilateral equiangular triangle has all 60-degree angles. 60 degrees, 60 degrees, 60 degrees. And if we drop the altitude down, that becomes a 30, 60, 90. And therefore, if the hypotenuse is S, the small leg will be S over 2. So the long leg of this right triangle is the altitude, and that's the short leg times √3. So that's S over 2 times √3. So the area of our triangle is 1/2 times the base times the height, which is 1/2 times S times the height of S over 2 √3. And therefore the area of any equilateral triangle will just be side squared times √3 over 4. All right, what if it's a regular four-gon? That's the easiest case in the world. A regular four-gon will be a square, so if you know the side length, the area is just side squared. What about a regular pentagon? So for the regular pentagon, what would its area be? All right, so this is where we get to our first substantial problem that's not trivial. There are a lot of ways of thinking about geometry, which is one of the reasons it's a great subject. I'm only going to introduce one way, which I think is a very nice, elegant way of finding the area of a regular pentagon, and that is dividing the pentagon into 5 congruent triangles using the center of the pentagon as the vertex of all 5 triangles. So you can see then that the area of the pentagon will just be 5 of those blue triangles. And since we know how to find the area of a triangle, we can find the area of this shaded blue triangle and multiply it by 5. And this is the same concept that will work even if it was a regular octagon or a regular decagon or a regular 17-gon. We can always divide a regular n-gon into n of these triangles. So if you can find the area of one of those triangles, then you just multiply it by n. So how will we find the area of a regular pentagon if its side length is S? Well, we already know that the base of this triangle is S. So for the triangle's area, 1/2 times base times height, we have 1/2 times S times, and we need to find the height. So how are we going to do that? If we look at our 5 triangles, going around one entire revolution is 360 degrees. So any one of those angles will be 360 divided by how many of them that there are? 72 degrees. So you can see 72, 72, 72, 72, 72 gives you 360. But our triangle needs an altitude which cuts that 72-degree angle in half. So we'll always take that result and divide it by 2, which gives us 36 degrees. And now if we focus on just the right triangle, we'll have to use SOHCAHTOA. So we've got this right triangle, which has a 36-degree angle, a 90-degree angle, and a 54-degree angle. We know that this entire orange side is S. So for the right triangle, that's half of S. And we need to know the height, which is this leg of the right triangle. So if we park at 54 degrees, you could park at 36 if you prefer. I'm going to park at 54. Then we want to know opposite and we know adjacent. O and A is OA, that's tangent of 54 is equal to the opposite side divided by the adjacent side. Multiplying both sides by S over 2, we know that the height is S over 2 tangent 54 degrees. So the area of this entire pentagon will be 5 triangles, where each triangle is 1/2 times the base times the altitude. Doing a little arithmetic, 5 times 1 times S is 5S squared on top, tangent of 54 degrees. And in the denominator, we have 2 times 2, which is 4, or 5/4 S squared, tangent of 54 degrees. Well, you know what's coming next. What about a regular 6-gon? So the process is going to look exactly the same, which is really nice. Divide the 6-gon into 6 congruent triangles. 1 full revolution is 360. When you divide that by 6, you get 60 degrees. You divide that by 2, we get 30 degrees. All right, so the area of the entire hexagon is 6 triangles, where each triangle is 1/2 times the base times the height. And the base is S, and the height is we don't know yet. So 6 triangles, 1/2 times the base times the height. Excuse me for a second while I make a correction. It's 6 of these triangles where the base is S. 6 of these triangles. So 1/2 times the base times H. All right, well, to find H, we're just going to use the special, we're not going to use SOHCAHTOA, we'll use the special right triangle relationships. And this 30, 60, 90, if this side here is S over 2, multiplying that by root 3 gives us the height. So the height is S over 2 root 3. And therefore, the area of the entire hexagon is 6 of those triangles, where each triangle is 1/2 times the base times the height. So we have 6 on top. 6 divided by 2 is 3. So we have 3 on top. 3 root 3. S times S is S squared. And on the bottom, we have 2. All right, moving on. What about a 12-gon? Now, at this stage, it's difficult to actually draw by hand an accurate 12-gon. So I was able to do it easily with this software because it can do 12-gons perfectly. But if I was doing this without software, I'd probably just make that picture. Knowing that this is the center right here, and knowing that the area of the entire 12-gon is just 12 of these triangles, I would just focus on one triangle. All right, so the side of this 12-gon is S units long. S, S, S all the way around. That gives us this dimension. We need to know the height of the triangle because remember, the area of this 12-gon will be 12 triangles where each triangle is 1/2 times the base times the height. So we need to know the height of this triangle. So we need to find these angle measures. So it's 360 divided by 12 is 20 degrees. But then this altitude split it in half. Don't forget to split that 20 degrees in half. So it's a 10-degree angle. So in our picture, as we're trying to find H, we have right triangles with a 10-degree angle, an 80-degree angle, and the right angle. And the side length of that triangle is cut in 2, so this part is S over 2. We need to know the height. We know S over 2, so when you're parked at 80 degrees, that's opposite over adjacent. So again, that's a tangent problem. Tangent of 80 degrees is equal to the opposite over the adjacent side. Multiplying by that orange denominator, we have S over 2 times tangent of 80 degrees is H. So the area of the entire 12-gon is 12 triangles, where each triangle has a base of S and a height of S over 2 tangent of 80 degrees. So 12 triangles, 1/2 times the base times the height. 12 times a half is 6. 6 times a half is 3. So we have 3. S times S is S squared, tangent of 80 degrees. The area is 3 side squared, tangent of 80 degrees. All right, it's time to start generalizing a little bit. What if all we know is that it has n sides, but we don't really know what that value is? It's impossible to draw that shape. However, we could draw one of the n triangles that makes up that shape. Recall that in the 12-gon, there's 12 of these triangles. So in an n-gon, there'll be n of those triangles. And we can draw one of them. And you might say, but we don't know how many sides there are, so we don't know how skinny it's going to be. Well, let's just not worry about that. If we aren't picky about what the shape actually looks like, if we don't care that it's not realistic, we can draw one representative triangle of the n triangles. And let's suppose we're actually given the height, so we're not going to have to find it this time. So there it is. We know that the side length is S, and the height is H, and this thing could have a million sides going around. We don't know, but we're just drawing one triangle. All right, the area of that regular n-gon will be n of these triangles areas. How do you find the area of a triangle? 1/2 times the base, which is a side length, times the height. So n triangles, 1/2 times base times height. We have 1/2 times h times n times s. I just changed the order a little bit. Each side length times n sides, that's actually perimeter. So we have 1/2 times the height times the perimeter, because ns is n sides, which is the perimeter. All right, so for any regular n-gon, if you just knew the perimeter and what the height was of any one of those triangles, then the area of the entire regular n-gon is just 1/2 times the height of that triangle times the perimeter. That was a general case. The process we went through was the same as the last two examples, so hopefully the process is starting to feel pretty natural to you. A couple of vocabulary words from 10.2. One is that pink segment from the center of a regular n-gon to the midpoint of any side, that's called an apothem. I've been calling it just the height of a rectangle, of a triangle, excuse me. Let me draw a picture of what we've been calling it. We've been looking at any one of these triangles, and we've been calling that pink segment the height. But there is another word for that. When you make a segment from a regular n-gon center to a side, to the midpoint of the side, perpendicular to that side, that is also called an apothem. And we'll use a as a variable. Now, we always have known that circles have a radius. Regular n-gons also have a radius, and it's the segment that goes from the center to a vertex. So this hexagon has 6 radii, and like a circle, it's from the center out to the edge, but it doesn't go to any old point on the edge. It has to go to a vertex. So that's a radius, and this is the apothem. All right, now we're going to do some examples. We're going to start with the circles and then move into some n-gons, and that's going to complete this lesson on 10.2. Let's begin with this problem. What if a circle's circumference is 20? Find its area. So we have two formulas. We have a formula for circumference, and we have a formula for area. And if they give you the circumference, which is 20, then we're going to start with this one. Circumference is 20 is equal to pi times diameter, or 2 pi radius. So the 20 is equal to 2 pi r, divide both sides by 2, divide both sides by pi, the radius is 10 over pi. Now why do we do this? Because we need to know the area, and the area requires that we know the radius. Well, now we know it. So now we can complete this problem. The area is equal to pi times the radius squared. 10 over pi squared is 100 over pi squared, and pi divided by pi squared leaves 1 pi factor in the denominator. So the area is 100 divided by pi. We all know pi is a little bit bigger than 3, so 100 divided by 3 is about 33. But if pi is a little bit bigger than that, then this will be a little bit smaller than 33. Next example. What's the area of a regular octagon whose radius is 50? All right, here we go. You could try to draw this regular octagon, but I'm just going to draw a single triangle where this is the center of the octagon. So the other sides go like this, but you don't have to actually draw them. Just draw a single triangle. All right, the area of this regular octagon will be 8 of those little triangles. Each triangle's area is 1/2 times base times height. So the area of our regular octagon will be 8 times 1/2 times base times height. We need to find those things. All right, we know that the radius is 50. So remember, the radius goes from the center to a vertex. That means this side is 50. So we need to know the height. We also need to know base. So we can't finish this problem until we know the base and the height. How are we going to do that? We're going to have to use SOHCAHTOA. How do we use SOHCAHTOA? We need to know some of the angles inside there. So remember this idea where an entire revolution is 360 degrees. So here we go. 360 degrees divided by 8 is equal to 45 degrees. But that's the entire angle from here to here, 45 degrees. So then we take that and divide it by 2, and that gives us 22.5 degrees. All right, now we can find these circles, this one and that one. Let's do the green one first. If we park at that 22.5 degree angle, SOHCAHTOA uses the green dimension, which is this long leg, and the hypotenuse. But when you're parked at this angle right here, which is 22.5 degrees, that's adjacent and hypotenuse. That's cosine. So cosine of 22.5 degrees is equal to the height. You could also call that apothem, divided by the hypotenuse. Multiplying both sides by 50, 50 cosine of 22.5 degrees is equal to h. And we've got this part done. Now we need to know what the base is equal to. All right, well, for that, we're going to have to find out this side. Now, that side is only half of the base. So once we find it, you can say b over 2, or we can just call this x if you prefer. Once we find that, we're going to have to double it to get the actual base of our blue triangle. So at 22.5 degrees, sine, cosine, or tangent of 22.5 degrees. Well, if we're parked by this blue angle here, that's going to be opposite in hypotenuse. That's the sine ratio. Sine of 22.5 degrees is equal to h over 50. So x is equal to 50 sine of 22.5 degrees. And therefore, this side length, which is b, we only found from here to here, so we have to double it to get b. So that would be 2 times that, which is 100 sine of 22.5 degrees. All right, now we have the base, so we can complete our problem. The area of this regular octagon is 8 triangles, where each triangle is 1/2 times base times height. We'll do a little bit of simplifying. 8 times 1/2 is 4. 4 times 50 is 200. And 200 times 100 is 20,000. So 20,000 sine of 22.5 degrees, cosine of 22.5 degrees. And there's our answer. 20,000 sine of 22.5 degrees, cosine 22.5 degrees. We could enter that into our calculator and get an approximation. But what we have right there is the exact answer. Entering this in my calculator, I get about 7,071.07 square units. Again, this is the exact answer, and this is just an approximation. All right. Couple more examples. What is the area of a regular nonagon whose perimeter is 400? Draw a single triangle, and there's 9 of those. Well, we need to know what the height of the triangle is. You could also call that the apothem. And we need to know what a side length is. In other words, for this one triangle out of 9 triangles, if we can find the area of this one triangle, we can multiply it by 9, and we'll have the area of the entire nonagon. So the area is 9 triangles, where each triangle is 1/2 times the base times the height. Okay, we need angle measures. So 360 degrees goes all the way around the center. When we divide that by 9 of these triangles, we get 40 degrees for each triangle's central angle. We divide that by 2. Each of these angles is 20 degrees, which makes these angles 70 degrees. All right, we need to know what the base is and what the height is, and then we'll be done with this problem. Well, in this problem, we're given the perimeter of 400. If it's a regular 9gon, then there's exactly 9 congruent sides. So base will just be equal to the entire perimeter divided by, oops, that's 400, divided by 9 sides, which is 44.4 repeating. That was nice. Now all we need is the height. All right, so in our triangle, we'll use one of the right triangles, which has a 20-degree angle and a 70-degree angle. And we know that the base is 44.2 repeating. So if you divide that by 2, the side is 22.2 repeating. And then in our right triangle, define H at the 70-degree angle. That's opposite and adjacent. So we have tangent 70 degrees is equal to the opposite side divided by the adjacent side. Therefore, the height of this triangle is 22.2 repeating, 22 2/9, times tangent of 70 degrees. So the area is equal to 9 times a half times 44.4 repeating times 22.2 repeating times tangent of 70 degrees. And that's the final answer, and it's perfectly exact. If we wanted to, we could put that all in our calculator, and we get approximately 12,211.01 square units. All right, for the next example, and this is the last example. A regular hexagon has an apothem of 8. Find its area. All right. So I'm going to draw that picture again. This is a hexagon, so there's 6 of these triangles. The apothem is 8. And the apothem is essentially the height of this right triangle. No problem. So the area of this irregular hexagon is 6 of these triangles, where each triangle is 1/2 times base times height. Height is 8. So all we need to do is find the base of this triangle. Remember, when we use SOHCAHTOA or special right triangles, we're using the right triangle, not the entire orange triangle. So in other words, we need to know the base of this orange triangle because there's 6 of those. But using SOHCAHTOA or special rights, the long leg is 8, but the short leg is only half of the base. So don't forget about that factor of 2 in the end. All right, here we go. All the way around the center point is 360 degrees. There are 6 sides to this. So 360 divided by 6 is 60 degrees. That's the central angle here, which means if you divide that by 2, we have 30-degree angles here and here, which means this is a special 30, 60, 90. So we won't be using SOHCAHTOA here. You could, but we should be always looking out for that special 30, 60, 90. All right, the long leg is 8. So the short leg times root 3 gives you 8. So 8 divided by root 3. And 8 divided by root 3, if we rationalize the denominator, is equal to 8 root 3 over 3. That means base of the orange triangle is 2 of those. So that was just for the yellow triangle's small leg, but we have to double that to get the base. So the base is equal to 2 of those, and 2 of those is equal to 16 radical 3 over 3. All right, so the area of our regular hexagon is 6 triangles, where each triangle is 1/2 times the base times the height. So the area is 6 times 1/2 is 3. That 3 divided by the 3 ends up being 1. So we're left with 16 times 8, which is 80, and 48, so 128 radical 3. That's the area of this regular hexagon. All right, if you haven't done that homework yet, or if you did it a long time ago, or if you had a lot of questions, please watch this video as much as it helps, attempt the homework, and then of course, please get ready to ask questions during office hours on Friday. And you're also welcome to send me emails with specific questions about the homework in general or specifically. All right, well, hopefully I'll see you in office hours. Otherwise, take care. Have a great weekend. And please keep in touch with the Google Classroom announcements at the daily. Take care.